Capacitors in series and parallel. Here we've got a simple series circuit involving a DC power supply and two capacitors, capacitor 1 and capacitor 2. To find the combined capacitance of these two, well, we know that the total voltage from the power supply is equal to the sum of the voltages across the two capacitors. So we can write that Vt, the total voltage, is equal to V1 plus V2. But from the capacitor equation we know that the voltage across a capacitor is given by the charge Q stored on the capacitor over the value of the capacitance C in farads. So we can substitute this expression into this to give the total charge over the total capacitance is equal to Q1 over C1 plus Q2 over C2. But the charge leaving one plate is the same as the charge entering another plate, so a certain amount of positive charge will leave the cell, travel onto this plate, making the same amount of charge leave this plate to enter this plate, and leave this plate to go back to the cell. So we can say that the total charge is equal to the charge on capacitor 1 and the charge on capacitor 2, allowing us to cancel the Q's to get 1 over the total capacitance is equal to 1 over capacitor 1 plus 1 over capacitor 2, and if we had n capacitors we'd add them all up to 1 over capacitor n. Don't forget to invert at the end of the calculation to find the total capacitance. As a quick check, the total capacitance will always be less than the value of the smallest capacitor in the circuit. Now let's look at parallel circuits. Here we've got capacitor 1 and capacitor 2 in parallel with the cell up here. In this case the charge leaving the cell will be shared between this plate and this plate. So we can say that the charge is shared between the branches of the parallel circuit. Or we can write the total charge leaving the cell is equal to the charge on capacitor 1 plus the charge on capacitor 2. But from the capacitor equation we know that charge is equal to capacitance times potential difference, allowing us to write the total capacitance multiplied by the potential difference is equal to capacitor 1 times potential difference 1 plus capacitor 2 times potential difference 2. But the potential difference is the same across each branch of a parallel circuit, or in this case across each capacitor, which we can write like this. The total voltage is the same as the voltage across 1 and the same as the voltage across 2. So we can cancel out the V's to get the total capacitance is equal to capacitor 1 plus capacitor 2, and if we had more capacitors, add them all together including capacitor N. As a quick check here, the total capacitance will always be greater than the value of the largest capacitor in the circuit. Let's look at an example. Find the total capacitance of the combination of capacitors here. Well, for the parallel capacitors, which I'll just put a box around here, we know that the total capacitance is simply the sum of the individual capacitances, which is 10 plus 15 microfarads, a total of 25 microfarads. What we now have is effectively a 25 microfarad capacitor in series with a 5 microfarad capacitor. So now for the whole circuit, I know that 1 over the total capacitance is 1 over capacitor 1, which I'll take as this one, plus 1 over capacitor 2, which I'll take as this combination. So it's equal to 1 over 5 microfarads plus 1 over 25 microfarads. Over a common denominator, this gives us 5 plus 1 over 25 microfarads. So now the important bit, don't forget to invert to find the total capacitance as 25 over 6 microfarads, or 4.2 microfarads.